I'm Stavros. This work was done between myself and my students. Pranav, who's the main driver for this project. Unfortunately, he's my PhD student. He couldn't make it due to visa problems. So I'll just walk you through our presentation here. Hand gestures. So hand gestures are a very good way to communicate that is non-verbal. They're very simple and efficient to understand. And a common and simple mode of human-device interaction based on computer vision. We could use computer vision to look at hand gestures in order to be able to determine what action we want. And it can be applied in many areas such as robotics, interaction with smart devices, as well as for enhancing accessibility. My research is really trying to deal with human-robot interface, HRI. So hand gestures are a simple way of trying to optimize that interface. So we were trying to start with identifying the hand gestures first, and then taking those, training the robot for the hand gestures in a Unity environment, which is a simulated environment, such that when you implement that robot with a human, you would not have any scenario, ideally, where the robot would damage the human. Right? So you do the training all in a simulated environment, train the robot. So what we're trying to do right now is collect all the images to be able to train the robot. Unfortunately, there's some challenges. The gestures vary widely and can have different meanings in different contexts. There's a lot of data that is required. The data is large and annotated data sets, but are often limited in diversity. So some examples here are that we have small sample sizes. So very similar to what you saw earlier with fixed medical images. There's not a lot of pictures of these online. There's a significant amount of racial bias. So we see a lot of pictures of white people, for example. We don't see a lot of people that may be African-American or African or maybe from South America. There's a lack of generalization. The environment in which we see them is not very generalized. People take images of these in front of white backgrounds, for example. That doesn't help very much. And that reduces the effectiveness of the data sets. Now, our approach to trying to solve some of this was to create these synthetic data sets, right? Given the fact that we don't have any real data sets that we would deal with, synthetic data sets should be able to help. Synthetic data sets are scalable and diverse. We can easily scale both the size as well as the diversity of the set. They are cost effective and relatively simple to build. I mean, you just use computers basically and you create a lot of new sets. And they do help a lot in training more generalized models. So the issues that we just described a minute ago, ideally, we would get addressed through these synthetic data sets. The issue is that there's a reality gap, and being able to bridge the gap between synthetic and real-world data still remains a significant challenge. So we decided to create a synthetic data set, and we did that for digits, ASL, which is American Sign Language, and hands in order to mimic the real data sets. This presentation examines the comparison between the results of the digit data set, showcasing the performance differences. We did publish the original hand gesture synthetic data sets earlier on in IM Drawings last year. You can see the difference that we were looking for here when we were comparing real versus synthetic data sets. Unfortunately, well, I guess I can use my mouse here to show people online. But between real and synthetics, you can see you get about 10x increase in the number of data that you have, the number of images that we have per classes, then the total number of images, since we had 15 classes that we did for each. And you can see that the data set, of course, explodes. This has an impact when it comes to training. I mean, training is going to be significantly lower, but the benefit is that you will have better training. Thus, you will be able to have a safer environment for that robot when the event eventually gets deployed. So we're looking at the digits data set. This is the example. This is what we published last year. We presented. So you can look at the first example, second, third, and fourth, for instance. And in all of these cases, you can see the actual data, which was the physical hand that you have there, and then the synthetic one that was right next to it. And that's what we were able to create in order to have the synthetic data set. The next thing that we wanted to do once we had this synthetic data set was to try different approaches. Given the fact that we had a very large data set and the slowness of being able to do training, we thought that one of the solutions here would be to use transfer learning, right? That would be able to have a frozen convolutional layer with ImageNet weights, and that would enable us to be able to run the training faster. That was at least our thought. And the second one was to use augmentation. So we wanted to see what would be the benefit of augmenting our original data set that we have. We used 3 different models. We tried VGG19, Inception, V3, and Exception. All 3 of these are pretty common, so that's why we used them. We used Atom for the optimizer, pretty standard data split. So a 60-20-20 between test and validation and training. And we used 2 different metrics, categorical accuracy, which is useful, but not without an F1 score. So that's why we got the F1 score also, in order to be able to give us some more confidence about the information that we got. Now I'm going to give you a lot of charts and plots of data, because that's really where the majority of this came. The training was done on GPUs, A100 GPUs that we had, and most of these runs took anywhere from 14 to 18 hours, just as a reference. Now, the first one is showing you training from scratch, and you would always get 2 different plots in these scenarios. The one with data augmentation is on the left, and the one without the data augmentation is on the right. So here's the data augmentation one, here's the one without data augmentation. And in this specific scenario, what's interesting is when training from scratch is that VGG19 seems to be able to outperform the other 2 models. You will see that in everything that follows after this, all the other comparisons, this is not the case. It's actually flipped. And we are trying to figure out why this is the case. We haven't necessarily come up with a very good answer to that yet. So this is just showing the actual data as we have obtained it. Now, what is plotted on these axes is the accuracy over F1 score, right? And that's what you're looking at, the y-axis. On the x-axis, it's a mix between real data and synthetic data, right? So as the percentage of synthetic data is added to the real data, you see that the actual accuracy over F1 score is going up, which is kind of what you wanted, all the way up to, in this case, up to 70. But in most of the scenarios, what we're seeing about 40 to 50 is an optimized mix between real and synthetic data in order to be able to get good results. And that's when we're starting to see the need of the curve in general. Now, splitting them out, just looking at the F1 score itself, just for reference, you can see that the F1 score is pretty reasonably high, but again, showing us this specific behavior of VGG19, which is unique when training from scratch. So now we apply transfer learning, and when we apply transfer learning, again, what I mentioned earlier is what we see is this behavior where VGG19 underperforms the other 2 models. And this will be consistent in all the other ones from here onwards. Now, in all of these cases, even in what we just looked at a minute ago, you will notice that data augmentation in general gives us better results than no data augmentation. This is one of the things that was consistent amongst all of these results. And again, we're looking at the F1 score here, again, consistently higher when you use data augmentations versus not data augmentation. Now, if we parse them for each one of these cases, right, and we do the comparison of all the possible permutations and combinations, right? So you have augmentation and transfer learning. Those are the two key items that we wanted to implement. So we can turn one on, the other one on, off, 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 on, whatever the case might be, right? And again, as in the previous scenario, which we noticed for the training from real data, VGG19 is the only one that slightly misbehaves. We're still seeing better behavior when we have augmentation on. This is a common across all three of these. But with VGG19, transfer learning on and augmentation on seems to behave better, right? Versus in all the other examples that we're seeing later on. So if we look at inception V3, if I was just to flip back and forth, just to kind of remind you, you'll see that the top two graphs are now flipped and they're now at the bottom. And that responds to the augmentation on, off, and the transfer learning being on, versus in the previous case, transfer learning being off actually behaved better than we see here. And this also applied to exception, very, very similar behavior as in the previous case. Here, we actually took the specific numbers rather than the plots. So you can actually see the mix of real versus synthetic data and where it behaves better. So at approximately a mix of about 70% of real data, we are seeing the best behavior for this model. If we move down and we look at data augmentation, again, we get this flip between VGG19 and exception versus exception. And you'll see again, though, at the same mix, at about 70%, we get the highest F1 score as well as the highest accuracy. With no data augmentation, you get a lower score. So that was, like I mentioned earlier, the common thread amongst all this data that we collected was that data augmentation helped us significantly in improving both the accuracy as well as the F1 score of all this data. And again, training from scratch with VGG19. So in summary, we looked at these different methods that we used in order to compare the results for the digit data sets for various cases. We used VGG19, inception V3, and exception for various percentages for real data mixed with synthetic training data. We had different settings with respect to transfer learning and no transfer learning. And what we noticed is that while VGG19 behaved differently than exception or inception V3, data augmentation across the board for all three of these seemed to always obtain better results. So our summary here was that mixing real synthetic data does help significantly. So we definitely want to use that synthetic data that we have. And in general, we want data augmentation applied, since that will overall improve our data that we will use for training the robot in order to be able to identify hand signals. And that was it. Any questions?
Very good work. Thank you for your work. Just have one question. Do you think your work can be further exploring the ability of sign language improvement or sign language tool to kind of developing a tool for people who use sign language to interpret it as from image to text or text to image?
Yeah, it could definitely be used for identifying sign language itself, since that's what it's really doing. I mean, if you really think about it, it's one step further than that. So the first thing that we have to identify is the sign itself. Then we have to take that one and train a robot with it. So it can definitely be applied for that aspect of it. Your second question with respect to can be used for image to text. Once you identify the sign, then you just have to have a good text production result, right? So that aspect of it, I guess, is independent, but theoretically it should be able to be done.
Yeah, it will be like two-step application or something like that to be
Yeah.
integrating this model. Very good work.
You're
Thank
right.
you.
Yep. Sorry, there was a question in the room too.
As far as I understood, training is conducted with synthetic data, but the validation for test is with the real data. Is that correct?
No, not necessarily. So what we do is we take the synthetic and the real data, we create a superset, right? And then we partition that superset so that 60% of it is used for training, and then 20% is used for test, and 20% for validation. Yes, yes.
Because classification, recognition is based on the static still pictures, right?
Correct. That is correct. Yes. So that's a very good point that you're making, which is our next step. What we want to do is be able to do localization, which is very specific to video. So if I have a motion, for example, I need to be able to localize that characteristic and then be able to do the recognition. We're not there yet. That is next coming up. So that will be our next step. So that's good question. Anything else? Sure.
Since different countries have different signs, different meanings of the gesture, right? So when you create the data sets, do you consider about this difference between the country?
Yeah, this is an interesting one. So this is where I started off. What we did originally is we limited to where is it? Sorry, I need to find the correct slide here. Here you go. So we used these three data sets. So for this one here, we use American Sign Language. So American Sign Language is American Sign Language. So if I use I don't know for sure, but let's say there's a Japanese Sign Language. I don't know that's a difference, but there could be one. Then you have to use a different data set, but you would follow the same process, right? So you start with that data, right, and then the real actual fingers. You create the synthetic data, then you can do the mix, then you augment that data, and then you can train, right? So the process is the same, but you would have a different set of real data that you would start
with. It's for the recognition, right? So if we recognize this gesture, it will the output it would be a test, right?
Correct.
Oh, okay.
Yeah, that's right. But it would be just specifically to that. So let's say, for instance, this gesture meant a go in ASL. I don't know what it means, by the way, but let's say it did, right? If in a different data set it meant stop, I would have to have that data set be used specifically for the action that I want in the end. Otherwise, I wouldn't be able to train my robot correctly.
Thank you very much.
Sure. Thank you.